Chapter 2 as discrete time system. We are going to look at a system. How do we define a system, discrete time system? Okay. The section that you will be covering here is discrete time system, block diagram. How do you develop a block diagram using discrete time system symbols? Difference equations. Then we classify the system. Then we look at the system with the various responses, and then we look at the stability of the system. Once you have understood the system, you can start to analyze. So let's look at a system. So what is a discrete time system mean? It's a discrete time system is a device, or you can call it, or it's an algorithm that operates on a discrete time signal, called discrete time system. So you give an input, pass through the system, you get an output. Symbolically, Yn is the output of a discrete time system, Xn is the input of the discrete time system, is going through the system H. So X is input, Y is output, H is the system. So that's the equation. So if you want to draw the diagram, here's your input, here's your output, here's your system. We must find difference equation for this in a minute. Sometimes you don't draw the block, you write this way, and put an arrow like that, and write the output. This stands for the system. System has to be described using difference equations, which we will come in a minute. In order to introduce a block diagram representation of a discrete time system, you must define some basic blocks. Like in electrical circuits, you need to have resistors, capacitors, inductors, cells, and everything in order to make a circuit. Similarly, in a discrete time system, you must have basic blocks. If you have the basic block, then you can actually interconnect them. You interconnect them such that you form a complex system. And I'll explain that in a minute. The first block that you need to know is an adder. What is an adder? You've got two signals coming in and being added and produce an output Yn. So the addition operation is memoryless. That means it doesn't remember what happened in the past. Whatever coming in now, two signals are added immediately. So instantly that's happening. So a block diagram is here. Here's an input. That's a discrete time input. This is another input, discrete time input. They are being added, and you get one output. So that plus that. Remember, this equation is only valid if one input and this input have same sampling period. The difference between samples are equal. If they're not equal, this addition cannot happen. They must have the sampling period T here, T must be same. If it is different, they will add up in a different positions, and they will not be, that's not correct. So for addition to happen, you must have same sampling period. Here is X1n is given by three values I've given. First is 4, 5, minus 3. These are the values at the different time instant. And the second input is minus 2, 4, 3. If you add them, you add the corresponding one. You add that one, and then you add this one, and you add that one. So if you have got three samples here, the output also should be three samples at the correct position. So 4 minus 2 is 2 at the position n equals 0. At the position n equals 0. Then 5 plus 4 is 9 at the position n equal to 1. And then those two added up is 0 at the position n equal to 2. You can see the positions are added up. 1, 1, 2, whatever the values are being added up, right? And they must have same sampling period, otherwise addition is not possible. The second basic element that you need to build up a difference equation or a complex system is a multiplier. Its multiplier is also memoryless. What happened to multiplier is that input is here and it's being multiplied by a number. Number could be a constant a, which may be less than 1 or greater than 1. And when you multiply the output yn, now it's become a times of xn. So that's a basic multiplier. So it's important, you need to have an adder, you need to have a multiplier. Right. Next one, next operation. So in the multiply operation, here's my input sequence. You see, that's the value. How many values? 1, 2, 3, 4. N goes from 0 to 3. This is my multiplier constant, 0.1. So the output is that multiplied by that is 0.2. That multiplied by that is 0.5 minus 0.5. That multiplied by that is 0.8 at the corresponding position. And the last one is 0.8. The next element, the third element, so simple, 3 elements, and then you can do anything you want. It's called a unit delay element. What does that mean? You take a sample and delay it by one sample. Unit means 1, unit delay means one sample. So if you take an input signal, xn, right, and if you pass it through a delay element, the output is going to be xn minus 1. That means it's delayed by one sample. So that's called delay element. So if you move on, I can show you the diagram. A symbol for a delay element is, this is wrong, that should be set to the minus 1, okay? And this is t. T is the sampling period. So you could say, you could represent by a sampling period, or you could represent by set to the minus 1. That is the minus 1. We'll come back to that later. They both give you 1 unit delay. So if you have the input xn, what's your output is going to be? Xn minus 1. So block diagram representing the unit time delay is t is the sampling period. And you could have 2 delays. You could have t, another t, and then it will be xn minus 2. So for example, if I have here 1 set to the minus 1, and then it passes through another 1. That is a minus 1. So if you look at this input is xn, and this output will be xn minus 2, because at that point is xn minus 1. So I've delayed once and twice. So you get xn minus 2. I've shown an example here. You can see this is xn, this xn minus 1, this is to the minus 1. Let's take the value xn. Xn was that. These are the value. How many value? 1, 2, 3, 4, 5, 6, 7, 8. So at different positions, at n equal to minus 1, xn was this. N equal to 0, it was that. I'm now delaying. Yn is xn minus 1. So what will happen is this one is now delayed. Yes, it's at minus 1. So when minus 1 is pushed by one sample, it will end up at y0. Is y minus 1. When you delay by one sample, it will end up at y0. So you can see that value at y0. This is now at 0, so it will be ended up in y1 because you're delayed. Right. This is at 1, it will end up with 2. So you can see these samples are being shifted every time. Check that again. So you will have, this is minus 1 and 0. So after it goes to the delay element, you will find that ends up at y0. So delayed by one sample. Okay? So that's what is being explained here in this diagram. Yn equal to xn minus 1. So y naught is equal to x naught. So you can actually substitute. If you want, you've got yn equal to xn minus 1. So you can actually substitute n equal to 0. So what happens? y0 will become x0 minus 1. What that means is x minus 1. So the x minus 1 value, which is x minus 1 value, that value, that's x minus 1, that value, is now ended up as y0, which is ending up here. So that's the way you substitute, and you can check them as well. So here is some examples of MATLAB code for you, delaying, multiplying, shifting, and everything. It's good for you to try these code so you've got a better understanding. And just to show you how you take a step unit, how do you shift this way and shift the other way. So you've got a few MATLAB code, which I'm not going to go through. You can just follow it up. Now we end up with a difference equation. Now that's the main part. We have to now form difference equation which describes the digital systems, right? A discrete time system, now you can say a discrete time system consists of what? Termination of adders, multipliers, and a unit delay. That's a discrete time system. We don't have differential equations, all difference equations. Now we can actually, so these equations would be ordinary algebraic equation if no delays were present. So difference equations are if you take algebraic equation, there is no delay. X squared plus 2x plus 3 is algebraic equation. If you take difference equation, there will be delay. So for example, you could have an algebraic equation like x squared plus 2x plus 1. In a difference equation, you will have x in, right, plus 2x in minus 1 and plus 3x in minus 2. So you have these delays there. So in difference equations, you will see that. In algebraic equation, you don't see it. So here is a couple of examples. Here is my example. I want a system where output input is delayed by 2 samples. So I have an input delayed by 1 sample, I got that. Delayed again, I get that. That's a delay. That's particular example. Let's move on to the next example. Here's an example I have. Have a look at this example. My output y is equal to half multiplied by input. My current output is equal to half multiplied by current input, quarter multiplied by previous input. This is previous, this is current, and this is current as well. And this is again quarter multiplied by previous input shifted by 2 samples, so delayed by 2 samples. This is previous input delayed by 2 samples, 1 sample, that's the current input. So how do we draw this particular difference equation? Now if I want to draw this difference equation, I need to actually draw this diagram very neatly and use the basic block elements, basic elements that we have talked about it. So if I now go and say, right, xn is what coming in, delay them, I get xn minus 1. I need xn minus 2, delay them, I get xn minus 2. Now I say half means I need a multiplier. Multiply by xn, so this goes in here, multiply, I get half xn. Then quarter is here, it's a multiplier, multiply by xn minus 1, I get quarter there. Then quarter multiply by xn minus 2, that's here. Add them all together, you get yn. So that's how you do the difference equation. So this is a difference equation, and this actually tells you about a system. And we don't know how it behaves. We don't know. We haven't learned it yet. But we are now trying to set up difference equations and to get a little bit of understanding. Here is another example. In this example, you can see yn equal to xn plus 0.25 yn minus 1. This means this is current output. This is current input. This is past output. You can see that. So if I draw this diagram, I got xn coming in here, then just throw yn there and take yn minus 1. So take yn, delay, and you get yn minus 1, multiply by 0.25, multiply by 0.25, add them to the xn. Xn is here, add them, you get yn. And you see the difference between these two equations. If you go back and just go back one slide, tell me the difference between this equation, this block, and this block. If you go back to this one, everything is feed forward. You see, everything is going this way. So add them together. This is called feed forward system. Everything is feed forwarding. That means feed forward system would have only current input, past input. If you go to the next one, you've got a input, and this is feedback system. Feedback system. Why? The equation has got previous output. So output is here. Previous means delay them and bring them back in. So it's a feedback system, and other one is feed forward system. Okay? So you've got two types of systems available. Now, if you apply the same thing, what about this system? Xn, 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 Xn. So there's no output coming in from past output. Current output is equal to, you add all these inputs. Therefore, that's also feed forward system. So if you look at next line, you are supposed to implement this yourself. So if you implement this one, what would you get? You get there 1 T, second block, third block, fourth block. Why? We need n minus 4. You say Xn, that's the minus 1, that's the minus 1, that's the minus 1, that's the minus 1. That's the representation of unit delay. And you take this output, you take that output, and take that output. So 1, 2, 3, 4. Now there's no second output. This is Xn minus 1. This is Xn minus 2. That's not an equation. So I don't need to take that output. Xn minus 2 is missing. I don't need it. So Xn minus 5 I don't need. Xn minus 3, yes, I need that. And Xn minus 4, I need that. So I take all these outputs, add them all, I get the output by n. So that's how, this is again feed forward system. You are feeding forward, nothing is coming backwards, okay? Here is another system you have. Now look at the system here. A node Xn, that's input is multiplied by a constant. A1 Xn minus 1, input is multiplied by delayed input. Then B1 Yn is minus 1. Output, delayed output is multiplied by B1 minus 1. So you have to implement, okay? Simplest way is start with Xn, right? Multiply by A node, multiply, so this is that part. Then A1 Xn minus 1, delay, here you will get Xn minus 1. Multiply by A1, you get this part done. That part, when you add them, this Bn is this. Now you say, okay, this is called the feed forward part. Feedback part is from here. So you take the output Yn, delay, Yn minus 1, delay, you get there, Yn minus 1 you will get. And that's multiplied by not B1, but minus B1. So it's multiplied by minus B1 and bring them back. So these are all bring them back, brought back. And this is already available here. These two are added together. You add them together, you get Yn. So feed forward part, feed forward, feedback are in here in this system. So feed forward part and feedback part are here. This is called direct form 1 structure. It's a direct form 1 structure is this. So coming back to the same system, I have drawn feed forward system followed by feedback system. And we can write the above difference equation as a set of two equations. So I could write the one equation that we had as Bn is equal to A naught multiplied by xn, that's that, plus xn minus 1 multiplied by a1, that's R1, that's called system 1. So I call this as system 1. Then the second equation, yn equal to Vn there, so I have the Vn there, Yn delayed is Yn minus 1 here, multiplied by minus 1, right, I have there, then add them together. So that plus that, I call that as system 2. Now you must know that these two systems, system 1 and system 2, are in cascade, C-A-S-C-A-D-E. They are one after another in a chain, cascade. If you have system, you have done systems analysis before, if you've got two systems in cascade, one after another, you can actually switch this system without affecting the output. You've got two systems here, you can switch them around like that. Put this in the front, this in the back. So you can actually do that. So I'm just demonstrating that here in the next slide. If I have a system 1 and system 2, I have got an input xn and an output yn. Important to know, I could move the system 2 here, that one in here. I will have a new input, new intermediate input, but for the same input, the output will be same exactly. So you can switch around this, nothing happens. Intermediate output will be different, but actual true output will be same. So if you have got a two systems in cascade, you can switch them around. Remember, it's very important. Without changing the input-output relationship, we can reverse the ordering of the two systems in cascade representation. It's very important that you can do this. So here is my system now. I've switched it now. Do you want to go back? I had earlier feed forward here, feed back there. Now I have put in from the equation feed back first, feed forward later. Go back here. Can I go back? Feed forward I have first, feed back afterwards. Now I put this system first. You see this one first and this one afterwards. Have a look. That's what I did. Feed back come in here and feed forward there. Earlier the feedback was from the output. Now it's intermediate. That's okay. It still works with that. You can switch this around and if you calculate the xn and a yn, for a particular xn, what's the yn, you will find they are same as the other system. So by changing around, you are not affecting anything. So you could now say to us, go back, well, what's the point? At that point and that point, I have the same, from there I'm tapping the same delay, you know. Now you can change around and say, why should I have two delay? Why can't I join these points together? So that's the next system. If you do that, you've got only one delay, and this part is feed forward, this becomes feed back, and the same system. So what have we achieved by moving around? Go back again, go back to the system. You have two delays, feed forward, two delays earlier. You switch the system around using the principle I've explained. And when you switch it, you got this system when you switched it. Now then you said you combine these two together. So when you did it, you got only one delay. So you have reduced your delay element. So this system implementation is a lot faster and very, very easy structure. This structure with the minimum delay, delay elements is called canonic. I think you can take out the AL. Canonic form. Canonic form means it's a structure which has got a minimum number of delays. So the previous structure that we had from here, this is not canonic because we got two delays there. You could actually combine them into single delay if it's canonic. So there's no need to delay operations. They can be combined into single delay as shown in figure 1. Since delay operations are implemented in memory in a computer, the implementation will require less memory. It can be proven that both block diagrams, this one and combining that one, are exactly same. You can prove that xn, yn, xn, yn. For the same xn, you can have this system. So you could have actually 3 systems really with the same thing. So if you want to prove that, we have to go back and write the equation and then say I've got 3 systems altogether. What's the system? I had first system. The equation was yn is equal to, what was the equation? Yn was equal to a0 xn plus a1 xn minus 1 then minus b1 yn minus 1. That's the equation. And if you look at this one, by switching the system, then you drew a diagram for this. The diagram was this one. This is your earlier representation was. This is the simplest system. Forward to backward. This is forward system, this is backward. Directly implementing this. Then you have shown that this equation can be modified this way. And then you showed combining this, you get a canonical. Now if you write the equation for that, you will find an equation in terms of Pn. See, this equation is, if you look at this equation, is in Yn, current output equal to A0 times of current input, A1 times of previous input, minus B1 times of previous output. They all added together to get the current input value, current value, right? So, this equation has got no Pn, no Pn. This one is not there. So, how are you going to start with this equation and then show that's equal to that? That's what we are trying to do. This structure is equal to this structure is equal to this structure. How are we going to show that? Next page shows it. It writes an equation for that. So how do you write the equation for it? Can you look at it? I have to write an equation for this. How do I write the equation? What is Pn? I can say Pn is equal to, yes, xn, right, that part, plus this one, this part, which is minus b1 Pn minus 1. So these two will now join together and they will become minus. So that will be minus minus P1, P1. Now you can write an equation for output Yn. If you write the equation for output Yn, which is equal to, have a look at the diagram, Pn multiplied by A0, Pn multiplied by A0, plus Pn minus 1 multiplied by A1, Pn minus 1 multiplied by A1. That's the one. So that means these two equations, you need to combine somehow, remove Pn, because that's an intermediate variable. Remove Pn, Pn minus 1, Pn minus 1, and Pn, and then show, when you remove that, your output is going to be Yn, your output is going to be A0 xn, this is what you have to show, plus A1 xn minus 1, plus, not plus, minus B1 Yn minus 1. That's the original equation. We have to show this from these two. If you show that, we can say all three structures I have drawn are equal. So next page does that. It's a small manipulation you have to do. This is what we want to prove. From the plot, from the diagram, that's are the equation which I wrote a few minutes ago. Now what you have to do, manipulate this equation somehow. And if you do it in a this is time domain. If you do it in a transform domain, it becomes simpler. But if you do it in time domain, you substitute n by n minus 1 in equation 2.4 on this one first. So wherever n, you put n minus 1. Wherever n, you put n minus 1. Wherever n, you put n minus 1, which will become n minus 2. Then you go to equation 2.5, take this equation 2.5, multiply by minus b1. So when you multiply b1 minus b1 that, and that, and that. So when you multiply all of that, is there a minus missing? Yeah, there's a minus missing. It's okay. You multiply minus b1, and once you have done that, you take this equation and look at the original equation, right? Go back. Adding equation 2.4 and 2.6. So you take this equation, add them is 2.4 again. What would you get? You will get, when you add this, you get yn plus b1 yn minus 1, which we wanted. We wanted to have that. Then you add this, you got this one and that one. We know by looking at these two equations, go back to your first equation, your Pn is this, and I can write, yes, that is my, from here I can write, from here I can write xn equal to what? You bring this one, Pn plus b1 Pn minus 1. So I can write that one. Going back here, I can write this one is equal to Pn b1 Pn minus 1. That is a naught is common, so a naught times of xn. Got that? Similarly, if you go back here, go back here, you can say what is Pn minus 1? Put n minus 1. Wherever n, you put n minus 1. What would you get? Equal to xn minus 1 here minus b1 Pn minus 2 you will get here. You see from here? And you can see from here xn minus 1 is xn minus 1 is equal to Pn minus 1 plus, bring this to other side, b1 Pn minus 2. And if you go to the next page, you see that part is a xn minus 1, a1 xn minus 1. So you got it now. That one is equal to that plus that. There's no b in it. So eventually you move to the other side, you show two equations. So now we know by manipulating we can say all three systems are same. All three systems are exactly same. Classification of discrete time system. Now we're going to classify the discrete time system into a couple of categories. Let's look at the categories. Next page. What are the categories to classify? What are the categories? We could have a static system. We could have a time invariant system. We could have a linear system, causal system, and a stable system. So we need to see what these systems are and why do we need to have this sort of properties or categories in order to analyze a system. Okay? So let's start with the first one. A static system. What is a static system? A static system is basically the current output. Look at the current output. Depends on the current input. But it does not depend on the past. It doesn't depend on, say, xn minus 1 or yn minus 1, n minus 2 or yn minus 1. It doesn't matter. It doesn't depend on the past. So there will be no current output if there's no input. That's the way it is. So if a system like that is called a static system, which has got no memory at all. Memory means past values. you remember the past, which is memory. You have built-in memory in the brain to remember the past value. In a system, it's like that. So statistics system is really pretty bad for us, because if you can't remember the past, then you can't really analyze the system. In a system, you want to know what happened in the past. You need to feed that information to design. You see? And this is of the another system, the memoryless system. Current output depends on the current input and current input cubed, but it doesn't depend on the past. So both systems these two are static and or memoryless. There's no memory. So for example, if you take a system here, yn is equal to xn plus xn minus 1. Yes. In this system, it has got a memory in it, xn minus 1. Even if you don't have this, there will be always an output from the past input, you see. Whereas here, if this is not there, output is 0. So that's the difference between memory system and a memoryless system. Take this one. This system, what we call it, is a dynamic system, or a system with a memory. Output depends on the current input plus past input. Similarly, output depends on n past input, current and n past input, n minus 1 past input. So that's the difference between a static system and a dynamic system. Dynamic system will have delay units, static system will not have delay. So let's take another one. Second one is time invariant. What is time invariant system? Why do you want to learn about time invariant? It's like this, simply. Here is a system. Here is my input, xn. This is my system, and this is my output, yn. If I delay my input by xn minus 1, my output also should be delayed as yn minus 1. Same delay. That's called time invariant. So if you delay the input by n naught sample, pass through the system, the output also delayed by n naught sample. That is called time invariant system. So we really want to have a dynamic system, memory system, plus time invariant. If you delay by 5 samples and the output delays by 2 samples or 3 samples or don't know, then it's very hard to analyze. So the system that we'll be learning is, if you delay by 5 samples, output will be delayed by 5 samples. So that's called time invariant system. The next one is in this case, determine if the system is time invariant. So yn is passing through h. H is given as n. So it's called nxn. So the response of the system is wn is equal to n times xn minus k. So I am delaying the input by k. This is what I get. That's what I would expect. Like if the system is correct, this is what you will expect. You delay your input by k, the output will be wn. Now, what's really happening is, look at this. When you take this equation, delay by n minus k, what happens? This also is delayed by n minus k, and that's also delayed by n minus k. So you'll have n minus k times that. When you multiply them out, you get that and that. So basically, this system is not same as what you want. Not same as this one. This is what you want, but that's not what you have. You've got another term here. Therefore, this is a time variant system. It's a time variant, not invariant. Invariant means you change input by 5 samples, output change by 5 samples. Time invariant means you change input by 2 samples, output might change by 8 samples. That's time variant. When the system is a linear system, you like to have linearity. You can add them together. You take one input, multiply by A1, take another input, multiply by A2, add them together, pass it through the system. The output will be A1 times of Y1, A2 times of Y2. So basically, we can add them. A1 and A2 are constant or arbitrary constant. That's called a linear system. Here is an example of a linear system, right? yn is equal to 1/3 xn plus 1 plus xn plus xn minus 1. We can write this as h xn. Xn is the input, h is the system. System is that different input. That's the system. You can write it that way. Or you say xn going to h is yn. Now let's start. How do I want to show this a linear system? I take the input x1 multiplied by a, x2 multiplied by b, and pass them through the system. When I pass them through the system, this is now going to be my input. So wherever xn plus 1, this will be a x1n plus 1, a x1n plus 1, plus b x2n plus 1, plus b x2n plus 1. Then xn is exactly same as that, plus xn minus 1. If you put xn minus 1, this will be a x1n minus 1 there, plus b x2n minus 1 there. Now you can see by grouping them, you can simply see this is going to be tau1, tau1, tau1. If you group that, what will happen? They will be ay1 because these are x1, x1, x1 corresponding to y1. If you group this one, that's by2. Therefore, it's a linear system. Very simple. So all you need to do, input has to be summation of two input, and then substitute that one here, and then group them, you get your linear system. In this case, you're proving as a linear system. Example here, is this a linear system? Okay, let's do the same. Yn is given as x squared. As soon as it's a square or cube, you know, you've learned in analog electronics, it's a non-linear system when you square it, okay? So let's prove this. So what do I have to do? I take my input as combination of two inputs. Now I go and substitute here. That's squared. That's my input squared. So multiply them out. If you give it a big line, that's not the case. Therefore, it's not equal to this. Therefore, it's not a. It's a non-linear system. So what we were expecting would be our output should have been, if it was correct, our output should have been a y1 squared plus b y2 squared in n. That should have been our output. But you can see it's not equal to a x1 squared. Yeah, it's also right. But you've got an additional term here. Therefore, it's a non-linear system. That shouldn't have been there at all. So it's a non-linear system. Sorry, this is not what we're doing. This is x1. Huh? Sorry about it. x1 and x. Can you see it? Here's another example. Let's take y equal to n xn. So what do I have to do? Make my xn as tau1 combination. Then let's go and substitute. Here by substitute an xn1 plus bn xn2. And I know by looking at it here, if this is xn so that's y. If this one is in x2, then it's y2. So it's a linear system, that system. So to prove this, you just need to practice. How do you prove it? Just a simple method of proving. Then the system we are going to learn is causal system. What's causal? Causal means that a system is causal if the output of the system at any time is a difference only in the present and past input, but does not depend on the future inputs. You can't say, like for example, if you write yn is equal to xn plus xn minus 1. That's a causal system, no problem, because it depends on the current and the past. But if you write another one, yn is equal to xn plus xn plus 1, then it depends on the future output. That's not a causal system. Causal system is this. This is current, this is past. That's this causal. Also, causal systems are defined as, here it is, a few examples. Is this a causal system? Yes. Is this a causal system? Yes. What about this one? No. Why? Because it's future output. Plus 4 means future value. So that's not a causal system. What about this one? It's non-causal. Why? X minus n. If you have, if that is your xn, x minus n will be like that. X minus n. Flipped around. So if you have, this means this side, remember, means all positive, like future. Or anything negative side is also, you can think it as future. That means that's non-causal. So you can say, basically, causal system means it depends on the past inputs. Or you could simply say a system is causal when t is greater than or equal to 0. All the values should be greater than n is greater than or equal to 0. Right? A system is causal. I have a diagram here. Is this system discrete time sequence causal? Another definition, if it has values or n less than 0. If these values are 0, when n is greater than 0, greater than or equal to, this is n is less than 0, then it's a causal system. It's all on the real axis, the positive axis. Negative is all 0, then it's a causal system. And also it's a stable system. Why? The output decays and go down. If the output goes and decays, then it's a stable system. If it doesn't go, increases, it's unstable system. Now, stable system. What is a stable system? You can have basically, if you give a bounded input to a system. So if I have a system here, and I give an input which is like a step input, which is bounded 0 to 1. And if my output is also bounded between 0 to 1, then I could say it's a stable system, but bounded input, bounded output, BIBO. That means I gave a bounded input, it gave me a bounded output. Then it is a stable system. So if your maximum value of input is less than or equal to A, and if your maximum value of output is less than or equal to B, and it's bounded means it's definitely less than a certain value, it's not infinity, therefore the system is stable. So a stable system will be only when input is bounded and the output is also bounded between two values, then it is stable. If output is increasing without bounding, without any boundaries, then it's unstable. Here is an example of a system. You've been asked to check this system. Is it BIBO? Do we know? But you have been told when y minus 1 is 0. That means when the negative time first sample is 0. So let's take this equation and see whether it's a bounded input, bounded output system. So how do you do that? So what you do is you start with an input of un. So I'm going to say my input is this. Right. My input is what? Basically 1, 2, 0, 1, 2, it points up. Then there 3, and that's 0, 0, minus 1, minus. This is a step input. This is my step input. So I'm going to start with that equation. N equals 0. What happened to y naught? Go back to the equation. What is the equation? This is the equation. N equals 0. Y naught is equal to 0 minus 0 plus x0. What is my x0? You go back there and see what's x0 is. X0 is, at that point, is 1. In the step, that's 1. So x0 is 1, so 1 is the answer. Now you go back, n equal to 1. So go back here, n equal to 1. y1 is equal to 1 times, so y0 plus x1. And what do you have? y0 you have already proved first time when you worked out it was 1. x1 is also 1 because step input, there, that one is also 1. So that's also 1. So 1 plus 1 is 2. Right, okay. So it goes to 2 next one. So second one is 2. Then when you do n equals to same thing, it goes 5. You can see it goes from 1, 2, 3, 4, 5. What will happen as you go along? It will keep increasing. the value will keep increasing. So it is increasing, therefore the system is unbounded. It's not bounded, so it's unstable. It's not going to be stable. So all the system that you will be studying from now onwards is linear system, time invariant system, and also most of the time you study causal system. Causal system means in the negative time the values are all zero, input values are all zero, and the output also zero. So that's the system you'll be studying. Now we are going to use transformation of discrete time signal. How are you going to transform discrete time signal? That's what we are going to do next. So in the linear time invariant system, we are going to look at some of its properties as well. We already know that if you take a signal xn and it will delay them, it will become xn minus k, to be delayed by k sample. If you advance them, it becomes xn plus k. I've already done this before. I explained you this earlier. Now we come to a signal, and we're going to represent the signal using impulses. Okay, let's have a look. Let's take a signal yn, which I can say any signal yn can be obtained by taking an xn signal and multiply by delta n minus k. What does that mean in this case? Let's take an example. Delta n minus k means delta n is like that point, n minus k means shifted. So at kth position you got an impulse, and I'm multiplying that impulse by xn. Xn is this. So what will happen if you multiply these two? Only at kth position this value will be maintained, all the others will be set to 0. So you can see the output in this case will give you all zeros except that. So if I now make this as delta n minus k plus 1, then this will be kept, all the others are 0. If I make this as delta n minus 2, then this will be kept, all these are gone. Depends on what you do. So if you apply this property, the property is shifting an impulse and multiplying with the original signal, you could represent any signal, a signal here Pn, I want to represent. How do you represent this signal Pn? Well, you could say, right, it has got a value here, it has got a value here, it has got a value here, it has got a value here. How do I represent this value? I will say, I take an impulse, shift them to that position, and multiply the whole lot by impulse. So I get a minus 3 multiplied by delta n plus 3 will give you that value only. Then how do I get this value? Take an impulse, shift to 1, delta n minus 1, multiply by the whole signal, I'll get a1. So I get that one. Then how do I get this a2? Take an impulse and shift by 2 and multiply by a2. Oh, the whole signal doesn't matter. You get that. Similarly, by doing that, you get individual values as my previous diagram. Now, if you add them all, that, you will get your original signal Pn. Your Pn comes into play. So we can say Pn can be obtained by taking this amplitude, multiply by a delta, this amplitude, multiply by delta, and so on, so on, so on. So any sequence can be made up of amplitudes multiplied by delta signal, which is shifted one way or the other. It's a good property. Now, if you make that as a general case, you could say xn, a signal input, can be made as xk multiplied by delta n minus k, its own value at that position, and sum them up. For real-time signal, first time you're coming across, there is no negative time, so k becomes 0. Have a look. That's called real-time signal. Now, you can say real-time signal with a finite number of samples, because discrete signals are sampled 1, 2, 3 up to 100, for example. So you say it is not infinity. You go from k equals 0 real-time signal, go to n minus 1, so it will be n samples, So any signal can be represented by its own value multiplied by delta n minus k. That means only kth position value is kept. Summation means next position and next position all are added up. I hope you understand. If not, just go through the slides again, try to figure out what we are trying to do. Basically, all I'm saying is that if you have a signal there, this is your signal xn, this is like 2, 3, 5, and this is xn. I can write this xn as like n is equal to, I could say 2, this is at 1, 2, 3, yeah? Xn equal to 2 multiplied by delta n minus 1 plus 3 multiplied by delta n minus 2 plus this side is 5. 5 multiplied by delta n minus 3. So a signal can be written in this delta form. Okay, that's got quite a powerful property there. So from now onwards, I could say now if I have a signal going from n1 samples this side and minus n2 samples this way, then I can say, all right, this is my signal. Now I can rewrite minus n2 plus n1, same thing what I did earlier. Every value multiplied by delta n minus k or n plus k. Now we come to properties. We could say we have learned before a special form of convolution. What we have learned now is it is called delta. What is convolution? Two signals, when you convolve them, that's the convolution sign, not a multiplication sign, the convolution sign. This is called convolution. That's defined as that, xk, yn minus k. Or, same thing can be defined, switching these things around, also you can define. So that's the convolution definition which you have done last year. And what I have done here also looks like convolution, but this is not y, but delta. So we are just setting up the equations for convolution and trying to get understanding. Later on we will use convolution. So in convolution, xn convolved, that's not multiplication, that's convolution, equal to yn is equal to yn convolved with xn. You can just switch them around in convolution, which is called commutative. Commutative means xn convolved by yn is equal to yn convolved with xn. Now we're going to look at impulse response of a system. LTI means linear. TI means time invariant. Do you remember what is time invariant mean? That means if you shift the input by 5 samples, output will shift by 5 samples. Linear, if you give the input A1x1, A2x2 add together, output will be A1y1 plus A2y2. So here's a system. You've been asked to find the impulse response. What does that mean, impulse response? That means you've got a system here. Here's a system, and you give an impulse like that. What happens to the system? How does it behave? Why do you give impulse? Next question, why do you give impulse? We showed earlier, impulse has got all frequencies. So I can actually, by hitting with an impulse to a system, all frequencies are going in, only some will come out possibly. So we can categorize the system. So always impulse response is very, very useful, very powerful technique, and analyzing a system using impulse response. I'm just getting tired of it, so I'm just raising this to get a little bit of rest. All right, let's move on. Here is a system for you, this system. Can you say what this looks like? I could just say this, yes. This is the feed forward part. There's a path forward, there's a path forward. And I can say this is feed back part. So I got a feed forward and a feed back together. So you have. Now I want to write an equation for this. So I could write an equation for this as this. I can say, here's my system. I'm going to say, if this is xn, what's the here? Xn minus 1. So what's here is bxn minus 1. So what about here? What will you get is axn plus bxn minus 1 there. And that's there sitting here. Then you've got a yn here. What's bn then? Write an equation for bn. Bn is equal to my yn coming here like that. So equal to yn, right? Plus this one. Plus axn plus bxn minus 1. And then we can write another equation relating yn and bn. How do you do that? You can say now yn equal to bn minus 1 c times bn minus 1. See? N minus 1. So we got 3, that's from here to here. So we got 3 equations. One set for that, one set for this, and the next set is for this. So there are the 3 equations you have at the moment. Using these 3 equations, I can actually find out the impulse response. One technique, this is time domain technique. Later on we'll do transform technique. So I wrote all the equation for you here. What I've written is that's one equation, that's the other equation. Once you have formed the equation, you can find the impulse response. Okay, go to the next page. What am I doing? I'm saying my input is equal to delta n. What does delta n means? Delta 0 is equal to 1, all the others. Delta 1 equals 0, delta 2 equal to 0, because impulse means only one value. Delta minus 1 also equals to 0, and so on. I am assuming Bn is 0 when n is less than 0. For negative n, Bn is 0. I am assuming initial conditions. So I am going to substitute n equal to 0. So I am going to go back to my equation and say I am substituting n equal to 0. What will I get? B naught is equal to A times x naught plus B times x minus 1 plus y naught. That's right. So I go back and see. How do I do that? X naught is 1 because that's the impulse. X minus 1 is 0, I showed you earlier. And y naught, what's y naught at the start? Is it 1 or is it 0? So go back and what did we give? They said y naught, y is 0. See, yn is initially 0. That means n less than 0 means y naught is equal to 0. So when I substitute all of them, this is 0, this is 0, this is 1, I get A. And then you go back, find out that's n equals 0. Now you want to find out, yn. So y1 equal to c times of v0. v0 is A, so y1 becomes AC. Same thing you repeat, n equal to 1. You say b1, ax1, ax naught, y1. y1 already available. X naught from now onwards is 0. Is it? Sorry. X naught is not 0. X naught is 1. Because that's an impulse. And x1 is 0 because impulse is here. Just 1 at naught. Then impulse becomes 0 here. All these places 0, 0, 0. This is 1, 2, and so on. This is minus 1. So that's 0. So when you add them, you get B plus AC. Therefore, y2, if you work out, that's that. If you continue this few more iterations, and the n equal to 2, check this one yourself, you get that. And if you do that, you will find for n equal to n minus 1, it becomes that. Just substitute wherever n minus 1. And then yn becomes this. Yn becomes C. There's a mistake here. This should be, this is wrong. That should be Cn minus 1. That should be Cn. Right? Eventually, once you've done that, you can now just say your output equal to, here's the output. When your input is an impulse, which from now onwards we call them Hn. That's a special name. If a system is called Hn, that means it's impulse response, which is equal to Vc, this is the answer. So what we are saying is, if you are given a system, here, you've been given a system here, Xn, Yn, and the output Yn is the same as the system's response when Xn is 1. That's what we are saying. When Xn is 1, the system response Hn becomes this for this particular system. So impulse response, Hn is called impulse response. So what you can do is, you can write these equations again and say that just go back here and write down here again. So you're saying Yn is defined as impulse Hn when the input is Xn. So you're saying if Xn is equal to delta n, then what you get in the output is called Hn. That is exactly that system's response. The system response is found out by giving an impulse to the system, and by observing the output. So give an impulse. If you don't know anything about the system, give an impulse at the input, look at the output, and write an equation for the output. That becomes the response, impulse response of the system. That is the system response. And Hn completely characterizes the system. So you've been given a black box, a difference equation inside there. You don't know how it behaves. So you give an input, which is an impulse. Work out the output and get an equation for that. That equation is the actual the black box equation, impulse response. That's what it's called. So from now onwards, we're going to say delta n. If I pass into a system, I get Hn, which is the impulse response. If I shift the input by k sample, output will shift because linear time invariance. If I now take this 2, if I multiply by Xn, Xk, you multiply here also Xk, no problem. Pass into the same system. Now you go to the next line. Now recall that Xn can be written as weighted sum of shifted sum. So if I now sum them up as k minus infinity plus infinity, passing through this, I will get the same thing with this. This is similar to a convolution equation. See that? We have learned that earlier. So what we are trying to say is that if you have Xn as an input to the system, and the output will be the input convolved with the system's impulse response, which is Hn. So basically, if I write that in the next line, go back to the next diagram. Here it is says, I can write an equation if you are given Yn equal to, right, Xn convolved with Hn. That equation always true. And how do you find Hn? You're going to say Hn is Yn when Xn equal to delta n. So you give delta here and an impulse, find out the output, that is actually the Hn. That's how you find the Hn. So before you write this equation, you have to find that. How do you find it? By giving an impulse, look at the output. Once you know that, you write this equation. So that's what is written here. There is a convolution. That means Xn, X minus, that's the actual equation. If you switch this around, that one comes here, that your equation also switches around. So that's the convolution equation that you have done. We have learnt about various systems so far. We looked at a system and found the impulse response. We know how to get impulse response of a system. What do you have to do? At the input, you give an impulse and go through that sequence equation and write an equation for the output. That becomes an impulse response. Okay? And within the system, there are two types and major types. There are other types as well, but we are going to look at two types. First one is called FIR system, which is called finite impulse response. So impulse response is finite. What does that mean? Let's take a system here. You can see in this system, this is a feed-forward system. That's forward, it's a feed-forward system. If you have a feed-forward system, like that, and what's the impulse response for a feed-forward system? And we can actually show, when we write the equation, we will show the impulse response of the system is going to be, right? That means I'm giving an impulse, this is 1 here, these are all 0. You write the equation for this and go through the procedure. You will find the first value coming out of the impulse response is, when you give this impulse, is 2. And the second value coming out of it is minus half. And third value comes out as 0, 4, 0, 5, 6, 0. All of these are 0, 0, 0, 0, 0. That means its impulse response is only 2 values after 0. Because it is finite, only 2 values or a couple of values gives you, it's called finite impulse response system. So you can simply say that, how do you show this? Okay, let me start to write the equation. What is Yn? Yn is equal to xn multiplied by 2 plus xn minus 1 multiplied by minus 2, add them together. So go in here, the equation, here this is, Yn is equal to that. Our input is delta n. Now let me say n equals 0, y0, x0, which is impulse response 0. You can simply hold that column. Y0 equals 2x0, minus 0.1 x minus 1, which is 0. Initially relaxed system, or impulse x minus 1 0. So it's 2. Then next time you do n equal to 1, work it out, you get minus 0.5. The next time you go n equal to 2, work it out, 2x2. x2 is 0, x1 is 0, so the output is 0. Because delta, remember delta, is only at that point is 1, other places all zeros. 1, 2, 3 values, minus 1, minus 2. Yeah? So if you continue this, it will be all zeros afterwards. So a finite impulse response system, which is a forward system, you will find only forward part would be there for finite impulse response. Everything is finite. In that case, the impulse response output is that and that, that and that, and then all zeros. If you've understood that very carefully, let's take a system Yn is equal to xn minus xn plus 2x n minus 1 plus 3x n minus 2 minus 4x n minus 3. What is the impulse response? That means xn is equal to delta n. What will happen to the output? Output is called at the time is Hn. You will find Hn will have first value would be the coefficient of that, which is 1. Then the second value is that, 2. Third value is going to be that, is 12. Make it 18. That. And the fourth value is minus 4. What is the fifth value going to be? 0, 0, 0, and 0. And this is at n equals 0. At n equals 1, and so on. So, for a finite impulse response system, the output is going to be the coefficient. That one, that one, that one, that one. And then it's also, that's why it's called finite impulse response. Because after some time it will go to 0. Infinite impulse response system. What is an infinite impulse response system? For an infinite impulse response system, there will be a feedback. So feed forward is all finite impulse. Feedback is all infinite impulse response. Let's give an impulse, 1. What happened to the system? You will find the output will never go to 0. It will always decay towards 0, but never be 0. It will be 0 at infinity. So let me write the equation for it. You know we have already done this equation. So I'll use that equation. The equation for that is Bn is equal to xn plus yn, and yn is equal to 1 times of Bn minus 1. Is that right? Am I right to say that? Yes, Bn is equal to xn plus yn, and then yn is equal to Bn minus 1. Yep. So if you have that, if xn is equal to delta n, calculate the impulse response hn. That's the question you have. So you go here and you substitute instead of yn here Bn minus 1 and rewrite the equation. You rewrite the equation as Bn is equal to xn plus Bn minus 1 plus, that's the one. Oh, that's a different, you need to redo this. You need to do this question. I haven't given a solution. So you can actually redo this question and you will find when you calculate hn is not going to go to 0 at all. So if you can't do it, just ask in the tutorial. I do one more example for you. Here is I have a system. I want to find the impulse response. My system is output equal to A times of previous output plus input. That's my system. And I've been told that xn equal delta n and apply 0 initial conditions. That means y0 equals 0 is given. Or y minus 1 is 0. So I have to write the equation. The equation is known. Ayn minus 1 plus xn. So you can say my equation yn is equal to Ayn minus 1 plus xn. Okay, I am substituting delta n equal to 1 and at n equals 0 the impulse. So I go n equals 0, y0 is equal to a, n0 is minus 1, delta 0. Previous value y is 0. Initially relaxed mean y is 0. So this is 1, so that's there. Then n equal to 1 you substitute. Your y1 equal to ay0 plus delta 1, this will be 0, but this is already 1, so it's a. Then you do the next one, this is wrong, this is a squared, right? Because y1 is equal to a and a multiplied, this is 0, a squared, and so on. When you do, if you keep going, you will end up with an equation where yn is equal to hn, this is not an, this is a to the n. The notes is correct, it's just the typo here. And if you plot this, what will it look like? If a is less than 1, to be like that. It will never go to 0, it will approach 0. So the impulse response of a first order system is that. So hence, hn equal to that. Why do you use un? If you plot an alone, if you put an alone, what will happen is it has got values there as well. If it's a real system, we don't need this. So we put un is a step function. If you multiply these two, this will go to 0. So that means it's a system for n is greater than or equal to 0. For all n, no, n is greater than. Real system is this. So my a is less than 1, it will decay like that. That's also. My a is greater than 1, it will go up. This is a stable system, this is an unstable system. But you can see both of them are real system, causal system. Causal means this part is all zeros. So I'm saying now, what is my impulse response? It's my xn. This is my impulse response. This is my output now. And if you take the equation, yn, what was the equation? A times of yn minus 1 plus xn was the equation. And if you draw the diagram, xn here, yn here, yn minus 1, a times, add them together, you get that equation. And also we can say yn is xn convolved with hn. So all these can be written by just writing the equation. But you now know for a feedback system, impulse response is infinite. Feed-forward system, impulse response is finite. So you've learned two systems, FIR, IIR. Here is an example. Find the impulse response of the fourth order, non-recursive. Recursive means, non-recursive means no feedback. So you can see it here, Yn output equal to A naught, no, that's not A naught, that's Xn, there's X missing. Oh, a lot of errors. Xn minus 1, Xn minus 2, Xn minus 3, Xn minus 4. Right. By looking at it, can you tell me what is Hn is going to be? Well, I can write it by looking at it. What's this going to be? If you give an impulse, this is all feed forward. There's no feedback. Why? There's no Y coming in. It's all X. So the output is going to be, first value is A naught, second value is A1, third value is A2, fourth value is A3, and the fifth value is A4. And the next is all 0, 0, and so on. Now that's your output is going to be. So by looking at it, you can write the impulse response. I have actually worked all the way through to show first is A naught, A1, then A2 comes in, then A3 comes in, then A4 comes in. After that, it will be all zeros. So I have actually worked through step by step for you to show, no. But if it's a feed-forward system only, by looking at the diagram, you should be able to write. Here is the system. Now, I draw the transfer function, not block diagram. This is the equation. First, x1, xn minus 1, xn minus 2, n minus 3, xn minus 4. And what, I don't know what values they have. This is A naught, A1, A2, A3, A4. Multiply and add them, you get your systems. Okay, we don't know whether they are positive or negative. Anyway, I just put values there. It could be positive or it could be negative, it could be anything. So these are the values. This is the impulse. When you give an impulse, this comes out first, then that comes out next, 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 and then 0 comes out, 0 comes out. Okay? So that's by looking at, this is a feed-forward system. Look at here, feed-forward. Feed forward, feed forward, feed forward, feed forward. There's no feedback. There is nothing from here that way. There's nothing. Therefore, feed forward system will have these coefficients as impulse response. Here's two structures. Write the difference equation. You've been asked to write the difference equation and calculate the impulse response. Now, basically, you can write the difference equation by here. Don't look at here, write them. When you write here, Yn, write into an order, and then see here is right. Yn is equal to xn plus xn minus 1 plus xn minus 2. So what's the impulse response? It's going to be Hn is going to be, first value is 1, second is 1, third is 1, and then 0 after that. What's the impulse response here? Oh, what's the same system? Oh my goodness. It wasn't supposed to be the same system. I think the second one hasn't got this out at all. It's not there. You can look at the notes. I think second one, this is missing. So the impulse response is going to be, for this one is, Hn is going to be 1, then 0, then 1, then all zeros comes afterwards. That's your impulse response. So I have drawn all the equation, write down the equation for this, and you know how this is, Yn, this Yn equal to this one, that's that part, plus this one, that's that part, plus this one, that's that part, that's xn minus 2. Okay? And I've just worked through them. You don't need to work through for all the question, but I've done it for you. And this one is right, there's nothing missing here. So there's something missing here, sorry. So write the equation, that's the equation. There's no xn minus 1, nothing. So impulse response will be 1, minus 1. Minus 1 is was the original question. So go back here and change this to, this is out, and this is minus 1, for the second structure. Oh, that's, yes, that's right. That's correct. Anyway, that's basically the impulse response. Just convolution, we have already done it. I just have to show you that convolution equation. Remember, two things are convolved. If you are given a box here like, and this is xn, this is hn, this is yn. The yn is convolved with xn and hn, and that means xk, hn minus k, you can expand it, and the other way around. This is commutative, that means you can convolve this one and that one exactly same. And associative means xn commuted with that and that is equal to these two first and this one afterwards. That and that first and that one. That's also an associative view. So here's an example where that two impulse responses are cascaded. So what is this equal to? These two convolve, you can write H1, H2 convolve, and X and Y. And what I'm trying to show is that if you have these, you can switch this around as well. You get H2 first, H1 second. That's another block. I have already gone through this before, but I'm just trying to get through this. Distributive law means they're in parallel. You have this one going through that, this one going through this, you can add them. So what does that mean? That means these two are added there, and you give input, you get the output. That's called distributive law. Right. It is important to know how to do convolution graphically. The reason is to get an understanding rather than doing the summation equation. Let's try this convolution. Here is the signal Hn, and here is the input signal Xn. This is the impulse response. You have been asked to convolve these two equations. So the convolution equation tells us that if you go back in time, what does it say? You take the impulse response, right, and you find out n minus k. That means you take impulse response, flip them, that will give you minus k, then shift by n will give you n minus k, and then multiply. So flip, shift, and then multiply. That's what it is. So here's the signal. So what I have to do first thing is I need to flip this. I have to, which will become h minus I. When I flip it, I have that there, that comes there, that comes here, that comes here. I flipped that. Now I have to shift it by n, or 2 samples, or 3 samples, doesn't matter. So I am shifting by 2 samples because I want to calculate the convolution y2. That's what I'm after. So I got shifted by 2 samples. That means everything is moved 2 samples. Once I have done that, I have to multiply. That's what it says. X I multiplied by h n minus I. That's what, and sum them. That's convolution. I'm setting it 2. So I'm trying to calculate what is h2 is equal to. You have to calculate every value. So h2 is equal to 2 there. Now you multiply this one with input. So you go back, you multiply that input by shifted by that one. So here, so all you're saying is now you add all these, that one plus that one plus that one plus all these are zeros. Whatever you add them and whatever the value you get is your h2. If you want h3, what you do? Same thing. You shift this by 3 and then multiply with the input and add them. So that is how the convolution is worked out. So if you continue this, your output will look like this, convoluted output. I have just shown you for a value, one value, y2 is one value you will get. So basically, this step 4 and step 5 are switched around. Sorry about it. In the slide, step 4 is here and step 5 should be there, right? This is y2. This is what, if you use the equation, Basically, I'm saying, here is my input, here is my impulse response. I want to convert. I flip this, right? Then shift it by 2, 3, 4 sample, whatever you want, H2 or Y2, and then multiply with this. Whatever I've left over, I add them. That's the value for that particular output. Then, same thing, flip, shift it by 3 samples, multiply with this, and whatever left over, add them. That's the next value. And similarly, Y2, Y3, Y4, you do. If you want Y3, you shift it by 3, and so on. That's how you do convolution graphically. So here's an exercise. This is your input Xn. This is your Hn. You do the convolution between both of them for 1 or 2 values. Once you have done it, check them. So you try it for Y2 and Y4 or something and see whether you get this value. And then you can, if you want it, use the MATLAB. Here's the MATLAB command I have written, and multiply on MATLAB command and plot them and have a look whether you get the same answer in MATLAB. You will get the same answer. So it's important to use the MATLAB as much as possible. This one you have done it last year, but I just want to run through this. You have been given one impulse response, another impulse response, 2 systems, and they are in cascade. And you've been asked to find out the overall impulse response. Find the overall impulse response, time invariant system. So how do you do that? We know we can write an equation that Pn is equal to that one convolve with that. Then you say Yn is equal to that one convolve with that. So you write those 2 equations. Pn, Yn is equal to these 2 H2, and that's when you substitute, you get Xn convolve with these 2 will give you Yn. So I have to find out Hn. Hn I know is equal to H1n convolve with H2n. But I have been given these 2 equations. I have been given. So I can find out easily. So what do? I've been given these 2 equations. So convolution means you write that one exactly. This one has to be flipped and shifted. So Hn minus k. That's the equation. So I go back to my own equation which is given for that. For that equation, I substitute. This one is as half k. This is given. Look at your notes. Times uk. Uk means that the negative part is all 0. Then H2 is also given. So it's n minus k you need to put in. That's also given. So instead of uk, it will be un minus k. You have done that. Once you have done that, now what happens is then you multiply these 2 together. So this is half k, this is 1/4 nk. And you will find now I'm going to remove this one and this one I'm going to remove. So I need to find out up to when this I can remove. You will find here uk means what? It's at kth place like that. Un minus k means it goes up to n minus k. So this is somewhere here. So you're going to go, these 2 means this is, so, oh sorry, just start the other way around, that's easy. You could say uk is like that, that's the normal, un minus k is like that. So basically you're going to say everything is going to start from n minus k, right? So you can say k starts from 0, and you want to make sure this has to be n minus k has to be always, this has to be greater than or equal to 0, because then only this will be 1. That means n is greater than or equal to k, therefore k should be less than or equal to n. And that's how I got the n here. So the infinity part, where is the infinity, disappears as soon as you remove these 2. So can I go through this again once more, if you didn't understand? Okay, just give me a second, I'll just go through this once more for you. I think the electronic board is getting tired a bit, I think, because doing all sort of things. This is infinity. This has to be n. When you remove these two, see that? How do you remove it? You know n minus k has to be greater than or equal to 0. Because then only you'll have 1 there, otherwise it will be 0. So n is greater than or equal to k. So k is less than or equal to n. That means the maximum value n. That's how you get the n there. That's how you work it out. So you now have these two together. So you can take out the variable is k, so you can take out n. So quarter n can come out of the sigma. That leaves you this. This is a power series. You know the summation of this is 2 to the power of n plus 1 minus 1. Is that right? So if you got to look at here, 1 plus r squared plus r cubed plus so on. This will be equal to 1 minus r to the n over, this is r n minus 1 here, over 1 minus r is the summation, r n minus 1 here I think. So I used that principle to find out this summation, which you've done last year, and the results become that. Again, if you're not sure about this, what I've done, you should look in the tutorial and it. But this should be fine. This is the same question. I don't know what happened here. I think I just wanted to show the students who don't know about that formula how I obtained it there. That's what I showed. And from that, this is what it is. The same question, I've gone through them again, and the answer is this one. And now you've got another example. You've been given this impulse response. You've been asked to find out yn for a particular input, I think. In this case, you have been given it's the same question. How do I determine the response of the relaxed system characterized by the impulse response? This, I think, in the input is also given in this case. The system. Can I have a look? Yes, the input is given in this case. Here is to a impulse response. The input is 2 to the n. It was not written here. Xn equal to 2 to the n. Look at your lecture notes. I think this is there. It's on the slides, is missing, but it's given in your lecture notes. Have a look at your lecture notes. And same principle I did. Same principle. When you want to remove these two, you must put n minus k is positive. And from that you find out n. And then this is the power series. And the summation of the power series is that. And you get the answer. Okay? That's just a simple example. We are almost there at the last chapter. And stability of a system. How do you do whether the system is stable or not? Well, give an impulse, and if the output is going up all the time, then it's unstable. Output decays, it's stable. That's the easiest way. But the other way of checking is, you can sum your impulse response, and if it is less than infinity, sum is finite. That's also an indication of a stable system. So let Xn be a bounded input, which is less than m. Bounded means we just got a maximum input and minimum. And we want to look at the output. So output is equal to the impulse response multiplied by the input. Input is given as less than or equal to m. So we go and substitute that. So when you substitute that, if you take the absolute value of both sides, what is the absolute value of yn? Because yn could be negative and positive, right? So that is your absolute value. We know this is less than or equal to, if you want to write it, yn is equal less than or equal to individual of the summation. That's the inequality principle. And using that, you could now go back. This is already known as m. So you can write down as is m times of this. And if this has got a finite sum, then the output is bounded. That's all it is. It's a basic kind of a derivation to show the output is bounded. But simply, if you give a bounded input, if the output is bounded, then it's stable. Or give an impulse, if the impulse response is not rising, it's only decaying, then it's also stable. Very simple to check. So here's an example. Check the stability of the first order spectral filter. And there is one A, and impulse response of the system B. Know the impulse response is that. We know we have done it. So we take the absolute value of this, S equal to sum them. If you sum this one, right, if you sum this one, the answer would be, is next. If A is less than 1, then that's your summation. And if the A is less than 1, this will go to a finite value. If A is greater than 1, then it will go, it will be unbounded, as I said here. For this summation to be true, or A should be less than 1. So now you got, what is question 4 here? Oh, sorry, this slide should be there. I forgot to release the slide. So basically, what you have here is the last part on that lecture, right? And I have gone through exactly what are the things that you need to know in this particular system, in particular chapter. Now we just look at the summary of the chapter. What have we learned in this chapter? You are expected to know all these. Remember, you tick these. Do you know the definition of a discrete time system? Think about it. Do I know what is a discrete time system? It's represented by a difference equation. It's not a differential equation, difference equation. So it accepts a discrete input and provides a discrete output. So what's the basic block of a discrete system? An adder, a multiplier, and a delay, unit delay unit. How to draw a block diagram of a discrete time system from a difference equation? I give a difference equation, you should be able to draw a block diagram. Important. Then how to write the difference equation from the block diagram? I give you a block diagram, you should be able to write the difference equation. Both ways. These are both ways you should be able to do. Then next one, the difference between the direct form. Now, 1, 2, and 3. I have shown you. Direct form 1 is forward first, back, feedback second. And then direct form 2 is feedback in the front and forward in the back. Direct form 3, or the canonic form, is to combine them and minimize the number of delays. So I've done that structure earlier. That's called direct form 1 and 2 and canonic form. Okay. And you need to be able to write the difference equation between all three of them and show all of them are same. Then you need to know the definition of static system, time invariant system, linear system, causal system, stable system. What are they? And the definition of them and proving them. Then you have to know interpretation of a discrete system. What are the weights? What are the constants? You need to know. Once you are done, you need to understand convolution. How do you convolve two signals if you are given? Then impulse response of a system, time invariant, how to calculate impulse response from a difference equation. What's the difference between an FIR and IIR system? You need to know. It's all I have explained. Then given the impulse response of a cascade of two cascade systems, compute the overall impulse response. I gave you two equations and you need to compute all overall difference equation. That basically covers everything on your second chapter, discrete time system. If you have gone through this lecture notes in the CD and then try to do the problems in the tutorial on your own before you go to the tutorial class, and you will get a really good understanding. If you have already know certain section on this, just move forward and move the bar and just skip some of the section. But first time I would say to you, go through them, all of them, and it's not important to go through all in one go. Go half an hour, then do another half an hour, and so on. Okay? Thank you.